In this video, we're going to derive the B matrix in terms of the isoparametric formulation. Remember, the B matrix relates our displacement vector to our strain vector. Recall what we've done so far. We have mapped our two-dimensional quadrilateral element that exists in XY space to a square element that exists in virtual ST space. In doing so, we found functions x and y, which are functions of S and t, meaning that they map a point that exists in ST space to a point in XY space. These functions are made up by a location vector which exists of the locations of our four nodes in XY coordinates times shape functions, which are functions of S and t. These functions ensure that any point that exists inside our square element in ST space will exist inside or be mapped to a point inside the quadrilateral inside of XT space. Just as we can relate a location in ST space to a location in XY space using these shape functions, we can also relate our displacement functions u and v through these same shape functions. So if I know location in ST space and I want to know the displacement at that location, I can map it the same way I mapped a location in ST space to my location in XY space. So what I'm saying here is that given my displacement vector, which remember is the vector I'm actually trying to solve for, but in my formulation I'm pretending I already know, multiplied by the same shape matrix, which consists of shape functions that are functions of S and t, that given in S and t, if I want to know the displacement that corresponds to what that ST location corresponds in XY space, where that displacement in XY space, how much that point is being displaced, I can find those displacements in a similar way. All right, so now I have my displacement function vector I'm trying to solve for times my shape functions, but these are now my shape functions in ST space. Remember, what I really want is I want to find a relationship between this vector and strain, and that's my B matrix. So let's take a look again at strain. My strain vector is this. It consists of my three components of strain in XY space. Strain in the X direction, normal strain in the Y direction, and shear strain in the XY directions. Remember, the definitions of these components of strain are du dx is strain in the X direction, dv dy is strain in the Y direction, and shear strain is du dx plus du dy plus dv dx. I'm going to do kind of a weird thing. I have a vector here, but I'm going to write this vector as a matrix, and you'll see in a second why. So I'm going to rewrite this vector as a matrix. The reason I'm writing this as a matrix is I'm going to pull out the u and the v, and I'm going to form what's called an operator matrix. Now, technically, this is no longer linear algebra because I'm not actually going to be multiplying u by d blank dx or d blank dy. Note the way I'm writing this here, I pulled the u's and the v's out and formed a vector. I'm going to treat this vector matrix in a similar way that I would treat vector matrix multiplication. But rather than, if there's an operator here, d blank dx, and remember the u is going to get in normal linear algebra multiplied by everything in this column. In the operator matrix, it just means that the u is going to be operated on by everything in this column. So here I will get du dx recovering the du dx here. In this column, I've got 0 operating on v. That just means it'll be du dx plus 0. Here I'll have u times, or operated on by 0, so I'll have 0 times u here, plus dv dy recovering what I have here in this vector. On the last row, I have du dy plus, by the rules of linear algebra, dv dx recovering my definition of shear strain. Okay? So now I have this, which I am calling an operator matrix. I now have a little problem. I don't actually have u and v. I have functions of u and v in terms of s and t multiplied by my displacement vector. So I can rewrite du dv times my operator matrix like this. Okay? So now I have my operator matrix times my shape functions, or shape matrix, in terms of s and t, times my displacement vector. I have a problem that I want to operate dn1, for example, dn1 dx, but n1 is not a function of x, it's not a function of y, it's a function of s and t. I'm going to clear up and explain how we're going to do that, but I need some more room on the board. So what I'm going to do is clean up the board a little bit. I'm going to take this final result and move it up here. Okay, so this again is just my final result I had down here. I have my strain vector as equal to my operator matrix times my shape matrix times my displacement vector. I was saying I have a problem that I want to take derivatives of these shape functions in terms of the derivatives in terms of x and y, but these aren't functions of x and y, they're functions of s and t. However, s and t are functions of x and y, which means if I want to take the derivatives with respect to x and y, I have to utilize the chain rule. In this case, my functions are functions of two variables, meaning I have to use a slightly more complex version of the chain rule that some of you may be used to. It'll have two terms in it. So for example, if I want to find dn ds, that is going to be equal to dn dx times dx ds plus dn dy dy ds. Similarly, if I want to find dn dt, that's going to be dn dx times dx dt plus dn dy dy dt. All right, so now I have two functions. They're both linear functions, so I could write this, if I wanted to, in a linear algebra form. I think I'm going to go ahead and do that. This is the same two equations now in linear algebra form. I have dn dx is equal to dn dx dx dn d plus dn dy times dy ds. That's exactly what I have here, and I could do the same thing for the second row. Note that I have a matrix here. It's a matrix of derivatives. This matrix is what I had mentioned before in a previous video. This matrix is called our Jacobian. All right, so now I have a way of relating our derivatives in ST space to our derivatives in XY space. However, what I'm looking for is a way to take derivatives in terms of dn dx. What I have here is a way to find derivatives of n with respect to s and t. If I want to recover this vector, what I need to do is I need to multiply both sides of this equation by the inverse of my Jacobian. Okay, so that'll end up with, on this side of the equation, I'll have the dn, dx, and dn, dy I'm looking for. And I need to figure out what I get on this side of the equation. I need to find the inverse of this matrix. It's a simple matrix. It's just a 2 by 2 matrix. How do I find the inverse of a 2 by 2 matrix? Remember from a linear algebra class, if I have a 2 by 2 matrix that's A, B, C, D, and I want its inverse, that is equal to 1 over the determinant times dA on the diagonal. I swap the A and D locations, and these become negative. So I have negative B, negative C. My determinant I can find as AD minus BC. Okay, so now that I've done this, I have a way of finding these functions dn, dx, or more generically, d blank dx and d blank dy. I'll save you some of the steps and just give you what the result is. Here, it's 1 over the determinant. Remember, so that is the determinant of my Jacobian. And if I take this, what I end up with in this row of my equation, I'll end up with this form for the derivative d blank dx and this form for the derivative d blank dy. I have d blank dx in my operator matrix here. I have d blank dy as my operator matrix here. All I need to do for my final step is substitute in these terms with these definitions here. Okay, so now I can relate my strain with all of this times my displacement vector. What that means is all of this, including the 1 over the determinant of the Jacobian, my operator matrix times my shape matrix, all of this is my B matrix, which relates my displacement vector to my strain vector. Note here, I've got a 3 by 2 being multiplied by a 2 by 8. That means my B matrix, as I expect, will be a 3 by 8. All right, now I know what my B matrix looks like. We're not going to go any further than that in deriving what our B matrix looks like. I do want to talk to you a little bit more about an easy way to find out what the determinant of our Jacobian looks like, and then just kind of show you our final form of our stiffness matrix in isoparametric formulation. We'll finish that up in the last video, which will be the last part of this lecture.